This talk is about moored ships in long period waves, and it arose out of some experimental work we did at the Institute of Ocean Technology in Newfoundland, Canada, a few years back. And so this is so we stumbled upon this instability quite coincidentally while we were doing the experiments. So I want to introduce the context today and then show you the experiments and kind of explain to you how we came upon this issue, and then go into the definition, background, and further investigation we did to understand what is actually happening in this problem. And then I'll finish off with some discussion and conclusions. So to give you a background, in the offshore oil and gas industry, a lot of more tankers are used for oil production because of their ability to store oil. So they are used quite prolifically in remote fields such as offshore Australia and in West Africa. So there are a number of regions where such more tankers are the preferred production choice. The terminology we use for that is FPSO, floating production, storage, and offloading vessels. And to keep them in station, they use different mooring techniques. The most common one are the single point mooring, either with an internal or an external turret. Although traditionally they used a lot of converted tankers, now there are more into new build FPSOs, and interestingly of different forms. There's a rectangular bar shape you would expect, but then there's also the circular FPSOs with very large diameter to draft ratio, almost approaching a value of 1. So a diameter is as large as the draft. So that's quite large FPSOs with big displacements. So to give you an idea of how these external and internal turrets look like, what you see are two FPSOs. This is a Laminaria FPSO, which is offshore Western Australia. And then the Kike is offshore Malaysia. And the Kike FPSO has an external turret here. And the Laminaria has this internal turret here. The lower part of the turret is actually a turntable, and the upper part is fixed to the hull. And through the turntable, the risers which carry the oil go through, and they are connected to the connections on the top through universal joints. The mooring lines are also connected to ferro lead points on the turntable. So the idea is, when there is a change of environment, the entire hull would rotate about the turntable. So the risers and the moorings are not affected by the rotation of the hull. So these are large structures, and you can see some human beings there. So they are quite massive structures. To give you an idea of what actually happens inside the water, so this one is quite a clear picture showing how some of these lines are connected here. So you can see the mooring lines are these catenary lines in groups of 3 or 4, and then these lazy shapes here, they are the flexible risers. They carry the oil and other condensate into the hull for processing, and they all go through the turret system inside the turret. And in this picture, you can also see a hull, a tanker there, which is an offloading tanker. So there is a hose that goes from the FPSO to the tanker for offloading the oil that's stored. So what is the industry practice? The principle behind the FPSO and the way the internal turret is located is that the FPSO will weather vane into the dominant load direction for directional stability. But the industry practice has found that the weather vaning ability is almost seasonal. It changes over the course of 1 year depending on which direction the waves and the swells come from. And quite often they find that there is loss of directional control when you have swells from a certain direction and seas from a different direction. In fact, there are cases where FPSOs need extra tug support to hold it in place for certain times of the year. The problem with loss of directional ability is that you end up with large roll motions because the FPSO would take waves beam on and resulting in process operations being affected. Like some certain separation modules will simply not function when the roll acceleration exceeds a certain value. So when we approached this problem, we were actually interested in examining the global performance of an FPSO in directional sea state. So we said we'll start by doing some experiments and then move on to numerical modeling. In our experiments, our ultimate goal is to study bidirectional sea states, swell and seas coming from different directions. So we went to the ocean basin in St. John's, Newfoundland, which has wave makers on 2 directions, 2 sides. Quite a very nice facility. There was an agreement between the National Research Council and the University of Western Australia, which allowed us to perform experiments over there. The facility is, the usable length is about a little over 50 meters, and the width of the facility is half of that, about 26 or so meters. The working water depth is about 3.5 meters. That's what we used in there. Wave making capabilities from 2 different directions, which allowed us to generate swell and seas from different directions. So the model we were using in our experiments was a VLCC with the overall length of close to 330 meters. The LPP is 318, the width is 56, and the working draft was about 10 meters. That was like a little over the ballast draft. So we were working with a displacement of close to 150,000 tons. So this is 1:60 scale model, which we use in our experiment. It's pretty close to the ballast, the lightship draft is what we used. You can see the hull floating over there. And they took a perfectly good model of a VLCC, and they drilled a hole in the front, much to the agony of some of the naval architects there. So they destroyed a perfectly good hull and put a turret there with a little turntable there. And the turntable had 4 fair lead points, about which, as you can see here, we had 4 mooring lines attached to that. And it was also instrumented with the load cells. So these mooring lines were basically fishing wires with the soft springs attached to them. And that was, since we did not have a target mooring condition we want to work with, we used kind of something that we tried to match some of the natural periods within a certain range. So we had a lot of flexibility in designing our system. So that gives you a picture of the layout. So we got the hull with the mooring lines. There's 4 mooring lines. They were symmetrically laid out, and they were all individually they were tested, and their stiffness was measured, and they were all we made sure they were all symmetric, and the stiffness was pretty close to each other, and you can also see a vertical view of that. prior to the experiment, we calibrated the wave system with the multiple array of probes, and because we were interested in a bidirectional C state, we had an array which was slightly rotated so we can measure the waves coming from different directions for later use. But prior to doing the random wave measurements, we wanted to get RAOs of the hull. And so we did a number of regular wave tests. And so we used the ITTC recommended wave heights and period in such a way that we maintained a constant wave steepness. So we started with the model with just the mooring lines, and we did some short duration runs, and we ended up with this. We found this instability, and later we tried to restrain the model with a soft line, and I'll talk a bit more about that when you see the video. And then we also did some long duration runs to see if the instability would go away later on. So we did a number of runs for a fixed wave steepness, and we also covered a few ranges around the natural periods and so on. So our main focus today is on these runs where the wave steepness is kept constant and a number of runs were conducted. So let's look at one of these runs. This is for a wave period of prototype wave period of about 15.4 seconds. So you can see what happens. This will be a few minutes. I should get that. So the FPSO is facing into the waves, and the waves are coming from right to left. These are very long period waves, regular waves. There's no random C state. There's just single wave, monochromatic wave coming from right to left, hitting the FPSO. And there's only moorings there. There's no restraint of any other type. You can see what's happening. People get excited. People are getting excited and saying that was my postdoc who was there. The hull actually drifts away from the head C condition and begins to take the waves beam on. Interestingly, it doesn't come back. It just stays there. And that's what we were more curious about, as to why doesn't it come back? Why is it staying right there? That's what we were more curious about. I'll stop it there. So that little time series you see there is what actually happens to the heading. So it initially is at a 0 angle, and then it starts going up, and then it oscillates a little bit, and then it stabilizes at some very large angle, close to 50 or 60 degrees. So this makes RAO evaluation very difficult when the angle is changing constantly, and RAO is a function of angle between the waves on the hull. So really, how can you get an RAO? So we were stumped. So we put some like a restraint in the stern, which is just like a single line, a very soft line. We held it from from yawing so much, so we can get a reasonable estimate of the RAO. And also, we then did a very long run. Well, this is actually one of the long runs. When we did the short run and we found this, we also did a long run to see what happens, whether the vessel will come back. We were hoping for that, but that didn't happen. So these are some sample time histories. This is the first one. This is actually a short duration run. The model is unrestrained. This is the restrained and the long duration run. This is one of those cases where the final heading is not too big. So it starts at close to 0 and then it drifts to about 6 degrees or so. And when we restrain it, we are able to contain it to within 2 or 3 degrees. And then even in the long duration, it went to about 5 degrees. But then there are other cases where the same thing happened for 50 and 60 degrees and so on. So really, what's happening here? So to do that, we went to the background, look at what are some fundamentals here. So we are basically interested in the yaw motion of the hull, which is designated eta 6. And eta 6 is also the angle between the wave and the hull, and the x-axis of the hull. An important parameter here is the location of the turret and the distance from the center line to the turret, A sub L. So the wave-induced response of moored structures, commonly we think about the linear response, which is a wave at the wave frequency, but we also have a number of nonlinear responses, the slow drift being the main one, and that comprises of the mean and the low frequency components. The high frequency response, which is also a nonlinear effect, is more important for structures like the tension-like platform. But it's the mean response which we are very interested in here. And they affect principally the surge, sway, and the yaw modes of motion. So to kind of give you an idea of how these mean forces come about, for example, if you look at the kinetic energy, even with the single monochromatic wave, the kinetic energy has a mean term, which is independent of time. And that then translates into a mean pressure and then a mean force. So this is a nonlinear effect coming from a single monochromatic wave. Another contribution comes from a wetted area change. So when you have pressure times area, which gives you the force, you could also have another nonlinear mean force contribution from it. So it's well established that mean forces arise out of regular monochromatic waves. What happens when you have a moored structure in waves? And this is a very interesting paper published in the Applied Ocean Research a few years back. And there the authors talk about the yaw equation of motion and how it can be decoupled under certain conditions from sway and others. And they show here the equation of motion, which comprises of the inertia term multiplying the yaw acceleration, and on the right hand side are the exciting forces. The inertia term has your usual yaw inertia, and it also has contributions from the sway yaw coupling, the suffix 2 for sway and 6 for yaw. And also here is the added mass in sway and the moment of inertia due to, or the parallel axis type moment about the turret axis. So on the right hand side, which is what I'm more interested in, are two moments. One is the drift moment, which is a mean moment from the waves in the yaw direction, which is M66. But then you also have the sway moment. The sway force induces a moment about the turret, which is M62. So we figure that when these two conflicting moments actually equate to 0, that's the point where the FPSO is kind of steady and stable. So if these two moments are conflicting each other, that is, they are opposing in signs, then there comes an angle where they actually cancel each other, so the FPSO is quite stable there. So we feel that this is how it happens. Initially, the FPSO is in the head C direction. Some sort of perturbation happens, as we saw in there when the guy screamed. Something happens, and then it starts drifting. We found in the experiments it drifts to the right or to the left of the wave direction. It didn't matter. So it drifts one way or the other. And as it's drifting, these two forces are actually changing because they are functions of angle. And they keep changing until there comes a point where these two forces are equal. And so the FPSO kind of sits there. So that's kind of the background. So we set out to see if this really is the case, and we wanted to verify that through a couple of numerical approaches. We went to the frequency domain approach because that was more straightforward and faster. We call that the quasi-dynamic approach, where you can actually calculate the mean drift force from your boundary element approach in a fixed heading at different frequencies. It's a linear method, amplitude independent. In the dynamic approach, which is a time domain approach, the mean drift force and moment are calculated, and then we use a time marching to get to the final angle. So in the I shouldn't call it quasi-static, it's quasi-dynamic. It's a boundary element method approach, which we use the WAMET program, which is part of the SESAM package from DNV. So you basically discretize the hull, and then you have monochromatic waves hitting the hull. You find the pressure due to various contributions, and then you integrate the pressure, the so-called near field solution, to get the mean force on the hull. And here I show you some results on these two the drift moments which I talked about before, M62, which is given by blue, and M66, which is the red. So for two different wave periods, 12 seconds and 13 seconds. What we see are characteristically different behavior. So in this case, what happens is the moments are actually equal to one another at an angle of 0. The x-axis denoting the angle. So they only intersect at the 0 angle. Whereas at 13 seconds, you see 3 points where they are actually equal. So, this is a very interesting situation. So what we find is, in this case, when the vessel oscillates about the 0, the blue line being below the red line, it's actually not restoring it if it goes to the left. And on the right hand side, it restores it. It's bigger than the red line, so it's actually restoring it. So it's what we call a stable equilibrium. So the restoring forces pull it back into the 0 angle. Whereas here, the situation is the reverse. So the restoring effect is not so strong at the 0 point. So a small disturbance basically allows the vessel to drift and keep drifting all the way until it reaches this 60-degree point, either plus or minus 60 degrees, where they are equal, and that's the point where it's actually stable and it just sits there. It doesn't come back. And that kind of explains why, even in the long duration experiment, the vessel doesn't come back to 0. It's just sitting there. So something interesting happens between 12 and 13 seconds, and that's shown here. You can look at the equilibrium angle in the y-axis and the wave period, and what we find is the solid angles, the solid markers which denote stable equilibrium Up until about 12.2 seconds, zero angle is stable. And then what happens is a bifurcation, and then you start seeing plus or minus 60 degrees as the more stable angle. So this is our, in nonlinear dynamics, you call this the pitchfork bifurcation, and there's a symmetric pattern happening about the x-axis. The zero angle is still there, but it's an unstable equilibrium. It's still there. So that was very interesting to find. We then went to dynamic analysis to see if we can see anything there. So we used the software Aqua, which has some very good time domain capabilities. It's a 6 degrees of freedom time stepping routine. We can actually introduce mooring lines here. So we mimicked the same mooring system as we had in the experiment, and then we conducted our simulations here. So in the time domain, we have to first do a frequency domain analysis, collect some of the coefficients, the hydrodynamic coefficients, and then we input that. Then the 6 degrees of freedom equation of motion is actually formulated with the wave exciting forces, mooring forces, any other force we may have, and then a convolution method is adopted for converting the coefficients from frequency domain to time domain, which incorporates the so-called memory effect. And then a time stepping routine is performed to get the position and velocity from the acceleration. So in our simulations, we used a time step of about 0.25 seconds. So we tried to get about 40 to 50 time steps per wave period. And we did a number of convergent tests and so on prior to conducting the simulations. So let's look at the results and see what we can make out of it. Both these simulations, the frequency domain and the time domain, demonstrated that there is an heading instability, and it's strongly dependent on the wavelength to ship length ratio. The zero heading is stable until the ratio is about 0.6. And then there is the onset of the heading instability. And then the heading angle increases to about 50 degrees, 50 to 70 degrees, for a range of wavelengths ranging from 0.6 to 1.8 times the ship length. And what we see is a characteristic signature like what I've shown here. This is an experimental result. Initially the zero angle, the vessel starts drifting, moves into a very high angle, and then it oscillates about that angle. So there is an initial overshoot which is then compensated, and then the vessel kind of stabilizes at some large angle. And this is something we saw quite consistently in a number of cases. So this is my the main figure from my paper. So I'll spend a few minutes talking about it. So this one shows the equilibrium angle versus the wavelength to ship length ratio. I've shown here experimental data, results from the frequency domain, which is the dashed line, and the time domain, which is the solid line. In experiments, we saw the vessel drifting both to the left and to the right of the head C condition. So we have just looked only at the magnitude. We haven't taken the positive and negative signs. We have put them together. So what we find in this case is the zero heading is preserved up until a certain wavelength, and then almost all three of them show the onset of instability at about the same point. So they show that from zero, the vessel goes unstable to about 70 degrees, and then it kind of remains in that general region up until about 1.8, the ratio of 1.8, and then there is some kind of a dip which is also shown in the experiments and the time domain. The solid line, the solid symbols are actually experimental data, but the open symbols correspond to the overshoot we saw in the experiments. which I showed in the previous slide. There's also in the experiments we did some long duration runs, which are shown in the orange, and the short duration run are shown in blue. The short duration line have one standard deviation error bar there, which denotes the fact that we could not always get converged results because of the short duration. But overall, we see a reasonable agreement between the numerics and the experiments, and actually the agreement is pretty good with the quasi-dynamic, that is a frequency domain, and the overshoot, the maximum angle we saw in the experiment. So that was pretty good. The time domain shows slightly lower angles than that, but it's well within the experimental data. And then it also shows the decrease, which is well captured by the time domain and the experimental data. So there is a lot of interesting things we saw from the simulation in comparison with the experiments. So contrary to what we expected, the simulation and the agreement kind of opened up a whole new list of questions. One of them was the effect of damping. The simulated results did not include viscous damping. The inviscid part, which is the wave radiation part, is naturally included in the time domain simulations, but we did not include any viscous damping. And the effect of viscous damping is what we are studying right now. We found that when you include viscous damping in sway and yaw, the final heading angle is preserved. But when we introduce it in other modes, in heave, roll, and pitch, you can actually alter the final heading angle. So this, we are still trying to understand what all this means, whether it's a program-related, software-related issue, or is it something physically real. So the ones we are more comfortable with are these two cases, which is the sway viscous damping and the yaw viscous damping. There are three different damping ratios we introduced and looked at how the simulation results look like. X-axis is time, y-axis is the yaw, and you can see the yaw kind of does the similar overshoot like what we saw in the experiments, and then it oscillates a bit and then stabilizes into some large angle. This angle is preserved for the three different damping ratios we looked at. So that was very interesting. These large oscillations, we do not understand it very well. They have 2,000, they range in period from 2,000 to 1,000 seconds. They seem to vary from cycle to cycle. So there's obviously some nonlinear aspects coming in. So to conclude, we find that ship-shaped FPSOs are susceptible to weather vaning instabilities when the wavelengths start approaching the ship length. And we think that this might get worse in complex sea states when you got swells from different directions from wind-driven seas, as well as you got winds and currents. So all those can complicate matters quite a bit. Good agreement we found between the numerics and the experiment on the onset and the magnitude of the final heading angle. The effect of viscous damping on the heading angle is currently being studied. So as part of this study, we also thought, is it wise to use ship-shaped vessels, which are designed to keep moving forward, to arrest them and put a mooring system on? So we are thinking maybe that's one of the contributions to, it's a wrong object used for a good purpose. So maybe the trend that's happening now is to go with circular FPSOs or a square shape or more block with a larger block coefficient. Those sort of things may actually help mitigate this problem. So I think the industry is kind of going in that direction. However, there's still a lot of large FPSOs, and somebody we were talking today, they are building floating liquefaction, LNG plants, which are about 500 meters long. So they are big islands out there floating in the water. So there are interesting problems like these we got to study. With that, I'll finish, and thank you very much.
Well, thank you, Professor. That was an interesting and timely paper in the offshore oil industry's interested FPSOs. And thank you. So I think the paper is very timely, very well presented. We have two discussers, so I'll ask one discusser who have prepared discussers, and then after we have the prepared discussions, I'll open up the discussions to the floor, and if we don't have any from the floor, I have a question I'd like to ask. So Commander Clippinger, could you come first and at the podium present yours, and we have one other.
I extend my thanks to the authors for their work discussing the theory, numerical simulation, and ultimately experimental validation of their numerical work. The thoroughness and attention to detail in the presentation and discussion of the experimental results is particularly apparent. It is well known that sway, yaw, and roll are linearly coupled and form the transverse motions of a vessel. The existence of a stable, the numerical and equal experimental results in the present work predict and demonstrate respectively the existence of a stable equilibrium in yaw at a large heading angle relative to the oncoming waves as the wavelength approaches the ship length. However, it appears that both the numerical and experimental programs included the simulation and measurement of modes of motion beside yaw, one of these being roll. If possible, could the authors comment even qualitatively on the amount of roll predicted by the numerical model and also discuss the behavior of the experimental model in roll? This seems to be the significant, as the authors themselves note, that it is the roll motions in particular that are the greatest interest to those engaged in onboard operations. Also, in the discussion section, the authors state that the trajectory of the vessel appears to be driven by some nonlinear effects surrounding the stable equilibrium. Could the authors discuss the extent to which these extensions of the present work will include investigations of these nonlinear effects, if that is their intention? Also, if possible, could the authors give their opinion on any additional linear effects, such as the presence of periodic coefficients, that may be considered as possibly contributing to the phenomenon that forms the subject of the paper?
So we thank Commander Clippinger for his interest and discussion of the paper. On the subject of roll motion, the oscillatory roll motion, along with other oscillations in the wave frequency range, is predicted by the program. And in fact, there is an earlier paper which I have cited in my written discussion, which reports on the comparison between the experiments and the simulation in this. In fact, it compares the RAOs between the numerics and the experiments. We found reasonable agreement, although the rotational motions showed better agreement than the translation. In terms of magnitude, we found the roll motions to be in the order of 5 to 10 degrees, and in some of the worst cases, it went up to 15 to 20 degrees. The yaw motion time history, which is what you were referring to kind of here, it exhibits certain oscillations, which is about the mean equilibrium position. We find that these have periods which are very long, and you see for these simulations the wave period is only about 17.5 seconds, and the x-axis scale is in the order of thousands of seconds. So we are not clear about how these large period oscillations happen. Presumably some sort of nonlinear effects happening there. So we may be able to look into it a bit more while we are doing the studies with changing damping and so on. Also, your question about periodic coefficients. We believe the nonlinearity discussed here is a manifestation of two conflicting exciting forces. So which change with the magnitude of the angle. So in a way, it's like it's the bifurcation is kind of dependent on these forces. In a way, it's like a basic parametric variation of these forces with respect to the angle. And if we can find these, what the relationship between the angle and the forces are, we can actually equate them and try to find analytically what the final heading angle is and how the bifurcation occurs. And our preliminary approach in this direction says that there are no periodic coefficients that are important. Thank you.
Yeah, thank you, Commander Clippinger, for your comment. And we have another comment from Piotr Van Dyke. So if you could come up.
First of all, I'd like to thank the authors for a very well-written and comprehensive paper. It's actually surprising how thorough it was from beginning to end to introducing the problem and giving a very rational and systematic approach to explaining some of the physics. So the authors have presented a very detailed look at the dynamics of weather veining and heading instability for an FPSO in regular waves. The model described is analyzed using two numerical approaches and compared to the experimental results. The quasi-dynamic analysis is very instructive, especially focusing on the wavelengths of interest where the unstable equilibrium and bifurcation are found. So in the time domain simulation, there's a clear presence of low and high frequency oscillation, as evident in actually these figures I think that we have up on the screen. It is suggested that the nonlinear effects cause the low frequency oscillations to change period as they decay. And my question is, do the authors have any insight about the high frequency oscillations in the signals? And I sort of hint at what I suspect may be going on here is that the encounter frequency is not really changing in this case, but they're using the approach of Cummins for retardation functions and convolution intervals requires accurate discretization and quadrature schemes and is based on linear inviscid damping coefficients, as the authors mention. And if the wave damping memory effects are important, the numerical methods should be carefully examined. And by that I mean that when you do the Cummins approach, it's typically on the seakeeping scale. So you're talking about frequencies of encounter that are related to the ship natural frequencies and the frequencies that you expect in the wave environment. Here we have very, very long periods of oscillation, and in terms of a numerical quadrature scheme, you have to be consider all of that. And the other comment I have is that the memory effects from diffraction may actually be important here, because that's the driving piece that will change as the heading changes throughout in the transient when it reaches as it's going to steady state. So the other question I have is regarding the viscous damping variations in the discussion section. The experimental results do not show any appreciable high frequency oscillations, suggesting that the numerical model lacking viscous effects is not sufficient. And can the viscous effects, other than the percentages that were described, which are instructive, can they be somehow related to sort of classical maneuvering coefficients and applied to the transient motion of the vessel as it rotates from its unstable equilibrium? And this might help in getting better agreements with the experiments. And again, thank you.
So the authors would like to thank Dr. Bandig for his interest and the comments. Since we have the figures here, the simulations we have shown here, like I mentioned before, for a wave period of 17.5 seconds, the time scales of oscillation, including what you refer to as high frequency, are still have a much bigger period than the wave period we are looking at. So they all, to me, the large oscillations as well as the little wiggles you see there are all much longer time scale than the wave period. So it's some nonlinear aspects which are coming into play, and we are fortunate that it didn't alter our discussion, because the final heading angle is unaltered. However, we take your point that, in fact, the comments you provided about the inviscid damping is very insightful to us, and it will help us with looking at how we can go forward with our analysis of the effect of damping. In fact, we find the effect of damping is critical to the magnitude of oscillations, as you see here, and the effect of viscous damping on the mean heading is also important, which we want to investigate further. And we feel that the viscous damping forces may dominate this scenario rather than the inviscid component. But as we all know, reliable estimates of damping is always very hard to come by. And so maybe we can relate the inviscid damping aspects to the maneuvering coefficients, as you mentioned, but we are looking at a zero fruit number case, so I don't know how that would pan out. But overall, this is a very interesting area that we would like to pursue, pending some funding. So that's kind of where it stands. Okay, thank you.
Well, thank you. And do we have any funding in the audience? Okay, do we have any questions from the audience? Comments? We have some comments. Okay, what I'm going to do is move the microphone over here so that people can come up and provide their comments. So if you can state your name and affiliation. Great.
I'm Tom Koster. I'm a naval architect, tanker naval architect who worked with MODEC for many years.
Okay.
And what I speak, I was taught by Sofek, the mooring designer for that company. First, I'll mention a comment about ship hull in support of the very, very good paper in your comment. Most permanent FPSO mooring designers would agree ship-shape hull forms L/B 5 to 6 are not optimal, but they are readily available,
Exactly.
and the places to build them have dry docks that fit that configuration. So I don't, except for the circular hulls, I don't see a big change in the near term. Secondly, if you superimpose wind and current, which are at different angles than the long period swells, the final yaw angle is generally much less than 60 degrees, on the order of 25 or 30. And the solution to the roll problem are deep bilge keels on the order of 1 to 1.5 meters, which increases the roll damping. There is an API code for mooring design, and I believe it gives guidance as to the design spreading between wind, wave, and current that you should use for the design. And it's true, the design generally focuses on the 100-year event, survivability in a 100-year event. And these large amplitude rolls occur in generally strange conditions. Hurricane has passed, wind is light, and the seas are on the beam. And finally, there are many, many West Africa and Brazil mooring systems which are spread moored to align with the swell, and that helps get rid of that problem. Thank you very much for your paper. It was very good.
Thank you very much for a lot of those comments, and they are very coming from someone from the industry. That's very insightful. While we were doing these experiments, we also had a chance to go to the Danish Hydraulic Institute, and which is now called Force Technology. I was talking with people there. They had a FPSO which they were testing in, and they found similar sort of heading instability problems, and they echoed what you just said, and that is when you put wind on it, it stops the heading from drifting like that, and wind actually for once helps in stabilizing things. So.
Bruce Hutchison, Gloucester Associates. First of all, and as noted, I think by both of the first written discussions, I don't think of this as an instability. I think of this as a stability. It's showing a stable behavior, and so it's kind of a symmetry breaking stability. It breaks the symmetry of head into the seas, but it goes to a stable condition. I'm a little confused about the discussion of damping in that the damping doesn't seem to affect the mean stable angle, but it does seem to suppress those longer oscillations, which appear to be some sort of subharmonic resonance. So I would be probably looking for some difference frequency phenomena, maybe leading to those oscillations. And I'm also a little confused about the definition of the damping ratio, since there's no obvious restoring force here. We don't have a critical damping, so I'm not sure what the percent damping is referred to. Maybe you can clarify that. Finally, and I can't remember the exact citation. It's now probably quite an old JSR paper, but I believe there was a JSR paper about 20 some odd years ago on a mooring instability, single point mooring. It was about dodging and it basically related it to a chaotic phenomena, so that why boats will dodge at their mooring, and that had a explanation in chaos theory. Thank you.
Thank you very much for those comments, and we are equally puzzled about the effect of damping in some of the simulations here. But we can understand that the oscillations which are happening about a mean value, they get suppressed by damping, and that's kind of, to some extent, you can kind of relate to that. I'm trying to look here as to how we define the damping ratio, and this was a question which one of the reviewers asked, and we addressed it in the paper. I just can't recall offhand. And your point is right. There is no natural frequency, so we had to use some estimate. If there is a written opportunity for this, I'll certainly include that in it. Yeah.
John Crosswhite, I'm also from the Boston Associates. I actually had two questions. Okay, sorry. I had two questions. One is, does the right-hand side, that delta, the delta between your M62 and your 66, presumably that changes with heading angle, yes?
Yes.
The actual magnitude of that.
Negative.
Now, if that provides an effective stiffness term, a yaw stiffness term, right, because your right-hand side is changing with angle,
Yes.
do you, just for a point of reference, do you have the natural frequency, and you also have a moment of inertia about your turret, do you know offhand what the natural frequency of that system is related to this? And my second question is, have you thought about the variations in like a 4/6 term? Like, do any of these oscillations relate to 4/6 type mass terms and how the model was loaded, like a gyroscopic effect, perhaps? Just curious.
Those are very good questions, and thank you. I'll answer the last one first. We did look quite a bit at the cross terms in the mass matrix and the inertia matrix, and we found that their effects was quite negligible. And we were actually hoping it wouldn't be, because that could explain some of that. The other point you made, that is very interesting, and that's something that would be worth investigating. And I can possibly look at this picture here, and I can maybe use this. So in other words, we are looking at how much is the difference between these two forces right here, and how rapidly will it bring it back to equilibrium, and that is a stiffness effect.
Yeah.
That could be that could actually answer the oscillation effects. So I'll definitely investigate that and see if I